So far, you've learned how to get the area under a curve using the integration method. So just a couple of things to note. Area can never be negative. It has to be positive. So if you were given a graph like this and you were asked to find the area bounded between the curve, which is this curve here, that would be a quartic, function. So bounded between the curve and the x-axis over the interval from A to B. So this time you can see the region they want you to find actually lies below the x-axis. And when a region lies below the x-axis, it is a negative region, okay? But area can't be negative. So therefore, you would use absolute value lines when you are getting the integral of the function from A up to B, okay? So absolute value lines will make sure that your area is positive. So anytime you see a region that lies below the x-axis, just make sure you're putting it into absolute value lines. Down here, if you were asked to find the area bounded between the curve f of x, and you can see that that curve starts up here and it goes down there, or it starts down there and it goes up here. So find the area bounded between the curve f of x and the x-axis. So that would be these two green shaded regions. And they've put the intervals on the x-axis. So from A to C is that little small region down here, which would be negative. So again, you're going to have to put that part in absolute value lines to make sure it's positive. And then this region would go from a lower interval of C up to an upper interval of B. Okay, and that would already be positive, so you don't have to put it into absolute value lines. So your equation would start off like this. The area would equal the absolute value of the integral of your function f of x with respect to x. And again, lower interval will be A and the upper interval will be C for that one. Absolute value lines makes it positive. Plus, you would then add on the area of this region. So it'll be the integral of your f of x function with respect to x from your lower interval of C up to your upper interval of B this time. And then you can just add your two answers when you get that done. So you are doing the two regions separately because of the fact that that one lies below the x-axis, but your intervals are on the x-axis. Okay, so that's just something to note. Okay, we look at the first example. Find the area bounded by the curve, which is a quadratic, x squared minus 9. So bounded between the curve, the x-axis, and the lines, x equals 0 and x equals 5. So I would always draw a quick sketch if they don't give you a diagram, which they normally would, but if they don't, you should still be able to sketch this yourself. So look, it's a quadratic, so you know it's positive, it's going to be U-shaped. They only want you to get the area under it between the x-axis and those two lines. Remember, x equals 0 is going to be a vertical line down through the x-axis at 0, and x equaling 5 is a vertical line down through the x-axis at 5. So my sketch would look something like this. Okay, so this region down here is a negative area, so I've just put a minus there, but this region will be positive. So we're going to have to do them separately, okay? Now, you're going to have to figure out what the numbers are on the x-axis. They are not given to you yet. But if you know the function, and I want to know where does that function cross over the x-axis, well, you're just looking for your x-intercept there, okay? So when a function crosses the x-axis, y would equal 0. So all you do is let your function equal 0. So that was your original function, x squared minus 9. Let that equal 0 and you will solve for x. So you can either do your factorization method, which will be the difference of two perfect squares, or you could also use your minus b formula. Either way, you're going to get two solutions for x. X is either plus 3 or x is minus 3. Now, based on our graph, because we are over the interval from 0 to 5, well, then it's not going to be minus 3, okay? So the other intercept we want is where it hits the x-axis at 3. So I now know that that value there is 3. So this region down here, the lower interval is going to be 0 and the upper interval is going to be 3. And then for this positive region here, the lower interval is going to be 3 and the upper interval is going to be 5, because that's what they said the two vertical lines were to go as far as. So this is the line x equals 0 and this is your line x equals 5. Okay, so that's your first port of call. You have to find the values on the x-axis that will be your lower and upper intervals if they don't give them to you directly. And all you'll do is find the x-intercept to see, well, where is it crossing the x-axis? Okay. Also then to know exactly, well, where is it crossing the y-axis? Well, sure, when it's crossing the y-axis, x is 0. So all you'd have to do then is let your x equal 0, sub 0 into that function, x squared minus 9, and you'll get back minus 9 for your value of y. Okay, so there's your substitution. So the y-intercept occurs at 0 minus 9 as a coordinate, so just mark that in there. So that's how I know how far down it went on the y-axis. Not that you need to know that, it's not necessarily, required, but I know that the rest of my quadratic, like, it would have turned and come back up that way like that. but that's not what I'm looking for because they made the restriction of the intervals between 0 and 5 on the x-axis, so I don't need that side of the graph. Okay, so I am now going to go off and get the integral. I'll do the two regions separately. So I'm going to get the integral of my y function from 0 up to 3, and I'll put it into absolute value lines because it is going to be negative. And I'll add on to that the integral of this region. Okay, so again, the integral of your function y from 3 up to 5 this time, and I'll be able to add my two answers together. Okay, so area is equal to the absolute value of, this is the first region which would have worked out to be negative. So your interval is going from 0 up to 3. Plus the second region was the positive region where your interval went from 3 up to 5. So if you integrate x squared minus 9 with respect to x, you're going to get back x cubed over 3 minus 9x. And obviously the same for the far side. So keep your absolute value lines. So it's now going to be the absolute value of, sub in your upper interval of 3 into the function, which is what I've done here. Take away your lower interval of 0 and keep your absolute value line on the outside. And when you tidy up that region, you'll get the absolute value of minus 18. See how it worked out to be negative? So we take the positive value of 18. Over here, so plus, I am now working out the second integral. So again, sub in your upper interval of 5 into the function and take away the lower interval of 3 that you subbed in. So this is when you sub in your upper interval of 5. That's what it works out to be, right? 5 cubed is 125. Minus, this is when you subbed in your lower interval of 3. And all of that big bracket works out to be, eventually, you'll have minus a third minus minus 18, which would be plus 18. So minus 3 and 1/3 plus 18. And then remember you had your positive 18 at the start, which gives you 32 and 2/3 units squared for area. So that would now be the area bounded between that curve and the lines x equals 0 and x equals 5. Okay, if we look at the following example, it says the diagram shows the curve y is equal to e to the power of minus x. So it's a negative exponential function. And part 1 says find AB. So find the coordinates AB, which is right here, where the curve cuts the y-axis. Now, when a curve cuts the y-axis, x is always going to be 0. Now, even if they had not said where the curve cuts the y-axis, you can see from the diagram, the point AB is literally the y-intercept. So all we have to do is let x equal 0 and we will solve for y. So my function was y was equal to e to the minus x. Therefore, it's going to be y is equal to e to the minus bracket 0. Minus 0 is just 0. So that's e to the power 0. And anything to the power of 0 is 1. So when x was 0, y has worked out to be 1. And as a coordinate, 0, 1 is your values for AB. So AB is equal to 0, 1. And I'd filled it into my diagram. I now know that that's 1 on the y-axis. Okay? Part 2, A of k is the area between the curve and the x-axis over the interval from 0 to k. So this yellow region is A of k, the area under the curve from 0 on the x-axis up to k on the x-axis. Show that the area can be given as 1 minus 1 over e to the power of k. So in order to get area, given that this is your function, we have to integrate that function. Okay, so I'm now going to get the integral of e to the power of minus x dx, all right, over the interval from 0 up to k. All right, so we are now going to go and integrate that. If you integrate an exponential, you will get back an exponential. So I'm going to get back e to the power of minus x, but then you have to divide that by the derivative of the power. If you differentiate minus x, well, that's a minus 1x, right? So if you differentiate minus 1x with respect to x, you'll just get back a minus 1. Now, you'd never leave a negative in your denominator, okay? So a plus divided by a minus is a minus. So it's going to be minus e to the power of minus x, okay? From an upper interval k, lower interval was 0. So there's no plus c constant integration because of it's the definite integral. So I am now going to work that out. So sub in the upper, so it's going to be minus e to the power of minus k. That's my upper interval. Take away, sub in the lower interval. So I'm subbing in 0 into that function. So it's going to be minus e to the power of minus 0. Close the bracket. Tidying that up, it's just going to be minus e to the power of minus k. Then here, that's just going to be 0. So that's minus e to the power of 0. E to the power of 0 is just 1. So this square bracket becomes minus 1. A minus by a minus is a plus. Okay. So we change the sign. So it's going to be minus e to the power of minus k plus 1. All right. Remember, they want me to get it looking like this. So I'll put the minus e to the power of minus k just on the right of it. So it'll be 1 minus e to the power of minus k. Then just take it out of negative indices. So that's an e to the power of minus k over 1. Just flip it upside down. And it'll become 1 over e to the power of a positive k. So that rule is in your log tables. All right. Where if you have a to the power of minus p, that can be written as 1 all over a to the power of plus p. Okay. So I've now gotten the area, a of k, is now equal to 1 minus 1 all over e to the power of k. So that was part 2 of the function. Part 3, find the limit of your a of k function. So that's your area function, okay, which we've already found to be this. So find the limit of that function as k tends towards infinity. Okay, so that's the limit as k tends towards infinity of 1 minus 1 all over e to the power of k. Right, well, as k gets bigger and bigger and bigger, because 1 is not dependent on k, 1 will just stay as 1. As k gets bigger and bigger, minus 1 all over e to the power of k. So you can test it. You could pick any random value for k. So like 1 all over e to the power of 2. So that'd be 1 all over e squared. Put it into your calculator. Then you could try 1 all over e to the power of 5. Put it into your calculator. 1 all over e to the power of 20. Put it into your calculator. And you'll notice that this fraction will always get smaller and smaller and smaller as k is getting bigger and bigger and bigger. So therefore, if it's getting smaller and smaller and smaller, it's tending towards 0. So 1 take away 0 is 1 unit squared, because it is limits what's it tending towards, and we're talking about area. The area is obviously tending towards 1 unit squared. Part 4, if a of k is equal to 0.3, find k. So if the area is equal to 0.3, we're looking for k. So I'm going to put down the formula for area that we just got, right, which was this value. So I'm just going to let that equal 0.3. So all we're solving now is an exponential equation. So I would bring the 1 over and subtract it. So you'll have 1 all over e to the power of k is equal to 0.3, take away 1. That would tidy up to be minus 0.7. Then you've got a negative on both sides. So I just multiply across there by minus 1, and that will change the signs. So you're then left at 1 all over e to the power of k is equal to a positive 0.7. Next, I'm going to flip this fraction upside down, so it'll become e to the power of minus k is equal to 0.7. And now you're trying to solve for k, so you have an unknown power in your index, so I have to introduce logs. I'm going to introduce the natural log, ln, on both sides. So minus k is now equal to ln 0.7, divide across by minus 1, and you will get k is now equal to 0.35667, ... goes on forever. So that's your value of k, which is accurate, because remember they had originally said k lies between, x, your interval, lies between 0 and k. So obviously, if that's the lower and that's the upper, well then this has to be a value greater than 0, which it is, 0.356. And they never asked you to round in the question, so that's your final answer for k. Okay, last example. If you are given a quad or a cubic function like this, and you're asked to find the area bound between the curve and the x-axis, but they've given you no numbers on the x-axis, well, you're going to have to figure out what those values are. Okay, now obviously that one's obvious, it's 0, but if it wasn't obvious, this is how you'd go about it. So the curve will intersect the x-axis at the x-intercepts, and when we look for the x-intercepts, we basically have to let y equal 0. So I'm going to let y equal 0, so I'm letting that function equal 0. Now, you can't do the trial and error method of trying to solve a cubic here, so all we can do is the factorization method. So I take out x, and I'm then left with a quadratic in the bracket, so there are your two factors. They both should equal 0, so therefore x is equal to 0, or the bracket is equal to 0. Go off then and solve the quadratic using the minus b formula or using the factorization method, and you will get out these two solutions. So these are all the three roots of that cubic function. So back up into my diagram, I can now place the -4 must be here, 0 is the origin, and this value here must be 1. Okay, so you had to find those two values because otherwise you can't get the area under the curve because you wouldn't know what the region was bounded in between. Okay, so now we're going to go off and get the integral of each region. So I've called this one region A and I've called this one region B. A is above the x-axis, so it'll be positive anyway, but B is below the x-axis, so it'll be negative. So therefore you're going to have to use your absolute value lines for region B. Okay, so it's going to be the area of region A first. So it's the integral of your cubic function, dx, from -4 up to 0, plus the absolute value of the integral of your cubic function, dx, from 0 up to 1. So that's lower interval, upper interval for region B. So I go off and I integrate that cubic function and I will get back this quartic function. And I'm just going to tidy it up because 3 would divide into 3 once and 2 goes into 4 twice. So you get x to the power 4 over 4 plus x cubed minus 2x squared. And that's your integral of the original function. So now I am going to sub in the upper interval of 0 and the lower interval of -4 for region A. Okay, and when I do that, I will eventually get out 0 minus a bracket minus 32. A minus by a minus is a plus. So the area of region A is 32 units squared. Then I come back and I go and get the area of region B, which was the absolute value of the integral of this function. So given that we've already integrated that function over here, I'm just going to write it down again. So it's the absolute value of this function from 0 up to 1. So sub in 1 as the upper interval, take away the substitution of 0, which is the lower interval. And when you tidy that up, it's going to be the absolute value of -3/4 minus 0, which just becomes the absolute value of -3/4. And again, area can't be negative, which is why we have our absolute value lines. So the area of region B is 3/4 units squared. The question would have said, find the area bound between the curve and the x-axis. That means it's the two regions together. So now I'm going to add 32 plus 3/4. So my final answer is 32.75 units squared for area. Okay. And that pretty much covers the vast majority of finding the area under a curve bounded between certain intervals.